Welcome to this Frequency Matters podcast. I'm Pat Hindle, and I'm talking today with Dr. Laila Salman, Principal Technical Specialist at ANSYS. Welcome, Laila.
Thank you.
So there's been quite a bit of excitement and news around 3D printed components, and using them in space applications also seems to be a very beneficial thing. So why is it such a good match for space applications?
Great question to start with the podcast. So when we talk about space industry or satellite communications payload, high power and lightweight RF passive components become very critical. And they are required to handle increasingly larger peak and average power over a range of frequency in the transmit path of the communication link. And this is where the additive manufacturing or 3D printing technology has matured as a breakthrough technology since it helps us or engineers to deliver and develop arbitrary shape RF and microwave components, where conventional machining can be either complex or even sometimes impossible to use. And it's anticipated to become the standard manufacturing technology that assures the production of these complex geometries where traditional subtractive manufacturing techniques may not be even applicable. It, Additive manufacturing or 3D printing had gained popularity, offering engineers and designers that flexibility to build customized and optimized designs with enhanced RF and thermal and mechanical performance. They can handle design trade-offs and maintaining precise mechanical construction of those RF components with their dimensions held to tight tolerances at that high frequencies, even up to 300 gigahertz. And we'll go through these in more details later on.
Yeah, I feel like the additive manufacturing has kind of had to help engineers relearn that now it's unlimited shapes that you can have, and you're not constrained by waveguide that's traditionally only been, right angles or, not as complicated geometries.
Exactly. And even consolidated different electrical functionalities in one part. And we'll discuss this a little bit later when we'll talk a little bit on more details about the additive manufacturing part.
Yeah, so what challenges do millimeter wave frequencies have in designing components compared to RF?
Well, that's a very good question. Now, let me answer you first by highlighting the application. So, as you may all know, 5G mobile network is expected to offer high-speed internet, high-definition video streaming, efficiency, and real-time connectivity to a larger number of IoT-based enabled devices. So promising connectivity at 3 times the speed of the 4G. Now, in order to achieve that, we have to start looking into new frequency ranges. So millimeter wave communication has become one of the most attractive techniques for 5G system implementations. Since it has the potential to achieve all these requirements and also enable a multi-gigabit per second throughputs. Now, with that in mind, the increased demand for building those complex RF passive components or at microwave and millimeter wave frequency bands that we've been talking about earlier. And that will bring up several design challenges. Since we have less room for manufacturing process tolerances with scaling the frequency. So smaller, non-tunable form factors with highly sensitive RF performance requirements, in addition to the manufacturing tolerances issues. Now, this is where exploring the usability of the 3D printing technology in the manufacturing process allows the engineers, like you said, to rethink of the RF design space and explore even variety of unrealizable design characteristics and aspects. And this is where altogether at the frequency of millimeter wave frequency bands, this is where altogether come and get together in a full design workflow.
So ANSYS has developed a workflow for waveguide filter design for the 5G space applications. Can you tell us about how this is done and, what was the impetus for developing this?
Yeah. 5G development has been driving the need for more filter designs in newer frequency bands, like we talked earlier, and new topologies uh, across even an ever increasing number of products. And as you know, microwave and millimeter wave filter designs have historically been handled by specialists. But with the increased demand for more innovative and complex filters, as well as consolidated electrical functionalities in one part to save the space and achieve compact designs, less experienced engineers need to get involved in the filter design workflow to achieve the throughput required for 5G implementation. Now, this is where ANSYS has put the effort and the expert into the software for EDA-enabled designs and help designers to experience performant designs with simulation capabilities. The team at ANSYS, along with our technology partners from Cinematrix, we developed an automated 3D modeling and optimization workflow that helps accelerate the development of filter design for 5G and other even RF and microwave communication applications in aerospace and defense, high technology, or high tech and automotive industries. Now, by integrating the ANSYS HFSS with the optimization algorithms from Cinematrix RF filtered software, the workflow becomes more intuitive and designs can be achieved more speedily, affordably, and even accurately, reducing that design cycle from sometimes weeks to days, especially with the use of AI-based optimization. Now, in addition to that, multi-physics theme or vision will come into the game as well, if we want to talk about this further later on.
And so why is it important to have this kind of workflow? What are the benefits?
Okay, so let's take a step back and just start emphasizing on the fact that RF filters are essential to a wide range of devices and applications. I mean, including broadcast radios, amplifiers, televisions, and wireless communications. So literally, you can think of RF filters as gatekeepers. They eliminate unwanted signals, frequencies, and noise that would otherwise cause interference or potential damage to the product and how it's intended to function. Now, this is why they have an important role in the overall system functionality and connectivity. Now, time to market and cost savings are impactful in product development life cycles. So smaller form factors, manufacturability concerns, and more sensitive design specifications can severely impact the R&D design cycle time. This is where an all-in-one solution workflow, like the one offered by ANSYS, can significantly accelerate the R&D cycle time. And just to close up on this point, I mean, the fact that our 3D filter design workflow connects naturally to other physics analysis and opens the door to realistic modeling with ANSYS Multiphysics and the other flagship products from ANSYS, where any variation in power level or surrounding environment can have a direct impact on the performance of these devices. So your design can immediately be tested by the industry's most highly validated thermal and mechanical physics-based analysis.
And you mentioned AI before. How is AI used in this workflow?
Yeah, so this is where when we need to meet design specifications, right? This is when we are going to be looking into optimization. So an AI-based optimization implemented in Cinematrix product, the core with the state-of-the-art reinforcement deep learning technique known as the AI tuning or the modified space mapping, those techniques are enabled to fine-tune those synthesized initial results. Now, both optimization algorithms are integrated with the 3D full wave solver finite element method solver within HFSS, and they can be even driven automatically. So there is a seamless integration. Now, this intelligent optimization usually starts with system perturbation to build up just the relationship, between the dimension, deviation, and the error information coming from the extracted coupling matrix. Once that initial slope information is estimated, the Iterated grouping optimization will start to diminish that error information based on the extracted error coupling matrix that is coming from the simulated S parameters. Just let me tell you that our machine learning is well tailored to the unique response sensitivities presented by the high frequency filter design, given that most of these dimensions and geometry design parameters can be extremely sensitive to any variation, while others may not, right? So introducing this AI-based optimization can definitely enrich the overall design workflow experience and tackle known optimization challenges for high Q and high order filters.
And you mentioned high power applications, where does the thermal analysis come into play and why is that critical?
Great question. So let me address this from two different angles: application and design to manufacturing process. Now, if I look into the application side, so we were talking about satellite communication, SATCOM, right? So then we know that the space environment is very extreme. Perhaps this is the most harsh environment one could develop a product to exist in. And satellites that pass from sun shadow to direct sunlit illumination can experience a very rapid temperature shift. For example, LEO satellites can experience orbital temperature differences from minus 65 Celsius to 128, 25 Celsius. Geosatellites can experience range of minus 196 Celsius to plus 128 Celsius in higher orbits. And all of this can be in a very short time. So temperature changes generally causes changes in mechanical dimensions, which cycle repeatedly during the payload's lifetime. Now, operating points for the thermal analysis that will enable us to anticipate the changes in material properties, including stretching, shrinking, right, which will turn to have a direct impact on the filter RF performance. Now, that is application. But if I take another look at the manufacturing process, and we've been talking about additive manufacturing process of these assemblies, during the process, internal mechanical support is required, and they can generate additional post-processing challenges. Once that optimal support structural topology and build orientation is obtained, coupled thermal structural analysis become very important to simulate the additive manufacture or the 3D printed build process and estimate the residual stresses in the build for a given, again, orientation and support strategy. This is very important in satellite communications technology, where any reduction in the payload weight is considered advantageous.
And so are there any special parameters or effects that need to be modeled, specific to the 3D printed process?
Yeah, well, like I said, I was talking about the build orientation, right? And the support. So during that 3D printing process, parts of the, if we take an example of the power bed, they melt when exposed to the laser intensity, subsequently solidify and experience transient thermal gradients. In subsequent passes for another layer in the vertical build direction, for example, the thermal gradient may create repeat softening for the frozen layer from the previous pass. Now, this thermal history during the build process influences the mechanical deformation of the part. Now, in addition to the laser scan pattern, the granular material properties of the power bed and the build orientation may both affect on the deformation of the part during the manufacturing process. As the deposited metal takes time to cool and attain the stiffness of the solid material, the solidifying metal may need to be supported physically. And this is where support structures can be cut off. They are needed, right, during the process. Then they can be cut off from the final assembly after the build process is completed. So the support may provide conductive heat transfer. Therefore, the optimum support strategy that creates minimum stresses in the part while supporting it adequately and while minimizing the support volume are both required. So from another side is the part orientation. It also can determine the build time. For example, if the part is oriented lengthwise along the build direction, so normal to the build plate, then that may require extra number of passes. So that will add to the overall build time. And while, for example, if we have solid support, are easy to design and more robust structurally, maybe the thin wall supports and lattices have minimal volume, and that will make them more efficient. So there are different parameters that definitely have an impact and an influence when we start looking and even thinking about the 3D printing process.
And so you were involved in a filter development process for a space application. Can you tell us about that project, the filter development and the results?
Yeah. So now since we all agreed about the importance of the RF filter in the overall system performance, taking shortcuts to compromise the design performance and meet schedule demands may also lead to design failures in the prototyping and the testing phases. So this is where having a coherent end-to-end solution workflow from 3D modeling to and 3D modeling and synthesis to optimization to RF analysis all the way to simulating the manufacturing process and addressing robustness and manufacturing tolerances along with the electrothermal structural deformation impacts. All of this is definitely valuable and can save weeks of design and test time for new filter development cycle. And definitely the first pass success can be assured this way. So this is what is great about the ANSYS automated workflow project that I have been involved in is that it incorporates several products and physics, and they can all be integrated seamlessly. And the results can be even circled back between those different analyses for optimal performance. Let me give you an example. I was working on a project, and um, let's say for a given operating frequency band and design topology, we started initially with the design, did the synthesis, the modeling, the 3D modeling. We exported that or generated the HFSS model, run the RF analysis, and because the high input power that will be pumped into the RF filter, we had to go for thermal analysis. So doing thermal analysis and looking at the temperature impact and geometry deformation, of course, with the ANSYS mechanical was very crucial because at the end, you want to make sure if that, because of the thermal or because of the temperature rising, if you take this information back from thermal analysis or even from structural for geometry deformation, if you take that back into HFSS, you want to know if that will end up adding or creating geometry or thermal drift, which will impact the RF performance. So there was a shift in the S parameters or the insertion loss of the filter, and we needed to compensate for that. And this was very important. Now, on another occasion where we were trying to design a filter and we already did the design, we did all the analysis, but then manufacturing tolerances is very important to consider. Design constraints. So this is when you need to make sure that you optimize across all the physics. And that was what this workflow is going to allow engineers to do.
And you mentioned first pass success. How did the simulated and measured parameters compare? And, were there any cause of variations in that?
Yeah, so for a prototype that was, or a work that I was involved in, and it's already published, the fabricated prototype successfully passed the quality inspection. Excellent correlation was obtained between the simulation and measurement, with a slight frequency shift that can be due to manufacturing tolerances or surface roughness. That's a new parameter that needs to be looked at and investigated, the surface roughness. So we actually ended up putting extra efforts on investigating possible causes of this slight frequency shift. Using the tolerance analysis, proceeding the Monte Carlo analysis to generate close to 300 dimension samples for each variable in the design based on the normal distribution. And we selected like 50, close to 50 dimension samples randomly to run the real EM solver. Now, from these simulation results, it can be seen that under a given tolerance value, the frequency shift can be in the range of 150 megahertz, while the return loss could be kept within the plus minus 5 dB. So yes, simulation did have a very good correlation with measurement. There were few, I would say, manufacturing tolerances or surface roughness. And then we looked into these, and we are still investigating more. But again, the workflow was able to get us a simulation or a design that did pass the first prototype.
Well, yeah, it sounds like you learned a lot in this whole process in the project. What's left to be done or future enhancements that are planned, like the surface roughness studies and multi-paction or anything like that that you hadn't considered previously?
Yes, yes. So, I mean, for the sake of design analysis completeness, definitely, like I said, space environment is the harshest the RF environment that you could design a part to operate in. So, studying space phenomena such as multipaction and microwave corona breakdowns are definitely in the plan, especially with the fact that we have a multi-paction and RF discharge solver capability within. It's built in inside ANSYS HFSS. So this is something that we already started working on it and started running those type of analysis. But like I was talking earlier, surface roughness, because surfaces of these printed parts can be rough due to the polishing or of irregular waveguide structures, uneven surface coating or corrugation of the surfaces while fabricating the waveguide, for example. And those will have an impact on the EM propagation, adding additional loss or dispersion effects. They can have an impact on the propagation constant and attenuation constant of the waveguide. They can change even the cutoff frequency for every waveguide mode. So it becomes very important to study the effect of the surface roughness on the electromagnetic wave propagation. Now, we can all also agree that the additive manufacturing technologies facilitated the implementation of monolithic waveguide subsystems, allowing the integration of multiple RF functionalities in a single part. The advantages of the manufacturing capability enables us to explore unique and optimized RF design characterizations and as well as assembly consolidation. I have a, I have come across research studies exploring like waveguide assemblies where multiple RF functionalities are integrated, right? Including, for example, bending, twisting, the filter section, all in one mechanical part. Again, the compact part. So given that ANSYS has the tools to create parameterized 3D geometries using ANSYS Discovery, and that can seamlessly be integrated in HFSS and the AI optimization from SynMatrix, right? All of these tools combined will help us explore new ideas of high power, high frequency 3D printed reduced weight waveguide assemblies. Consolidated RF functionalities in one part. So now having this automated workflow has been already adopted, to be honest, by several companies. And it involves the collaboration between product designers, engineers, analysts across geographical and functional silos, right, in different physics. So there will be always this need of that platform that will boost engineering productivity by democratizing the simulation process and the data management. And this is where I was thinking that, okay, now I have a workflow, an automated workflow. If uh, somebody would like to use it and adopt it, right, then it will involve the engagement and the collaboration of multiple teams. So why not of using an enterprise level SPDM solution that will secure that those critical simulation data, provide simulation process and decision support in both on premise or cloud deployment ecosystem, do project management. And this is what ANSYS Minerva is actually going to provide us. So there are few, I would say, future work to be done. Like I said, to summarize it, from surface roughness to multi-paction to looking into the ANSYS Minerva for project management and data management as well, and even more. We have because we are involved with the additive manufacturing, so this way which material to use for the 3D printing, you need all the information and the I would say the vendor information of all these material, all the physics properties to be included, and that's also something that we offer with Granta. So and we can read those material properties from Granta also seamlessly. So those are stay tuned for new publications on that will tackle all of these studies.
Well, excellent. Thank you so much, Dr. Salman, for talking with me today about the workflow for simulation projects like this for space applications. It's been very interesting and a great area that ANSYS has done a lot of work in. So appreciate your insights, and hopefully we can catch up with you in the future as this develops.
It's always my pleasure, Patrick. Thank you so much for hosting me.
And to our listeners, you can find more podcasts at podcast.microwavejournal.com. Thanks for listening.